Welcome to Lunch with Larry. Today we're going to talk about systems modeling and why it's so important to integrate your risk management with your systems models. Let's get some lunch. So we're going to start our systems engineering discussion using the example of the Boeing MAX crashes that happened here a couple years ago. I'm going to start with a couple quotes, and we're going to talk through how it is this kind of problem can occur and how to construct some systems around the different controls and requirements in order to better control, better understand the implication of any particular change that we're going to make. The MAX crashes were not a result of a technical failure, technical mistake, or mismanaged event. Now, this is from the NTSB. And this is the kind of language we start to see when we talk about systems failures. There's a great variety of different things. There's mechanical sensors. There's software involved. There's the users of the pilots of the aircraft. And when we start to compile all these different views or different inputs into the system, what happens is a particular combination creates a real catastrophic failure. So a very common language. The next quote is, "The problem is it was compliant and not safe and people died." This kind of speaks to how risk management needs to be integrated into the discussion. So not only do we need to have a systems engineering view where we're decomposing the design to understand what the positive view of the design is, what does the design need to do, how are we going to provide the value to our clients, but in addition to that, we need to have a negative view of the design. How can this design fail, and what systems and design and specifications controls need to be in place to assure that that problem does not occur. And so it's very important that we not only take this positive view, but we also have different frameworks to look at. And so the NTSB provided a root cause as a result of this. So this is all public information, but it says the House Committee's report examines Boeing engineering and technical design flaws, especially in developing a new flight control system called the Maneuvering Characteristic System, or MCAS. Early investigations found that in both the Lion Air and Ethiopian airline crashes, faulty data from a single angle of attack sensor caused MCAS to force the plane into repeated nosedives. So MCAS is software. The angle of attack sensor is an input into that software, and it forced it into repeated nosedives that the pilots eventually couldn't pull out of. The report also details the faulty and outdated assumptions engineers made about how pilots would react in such a crisis and how Boeing failed to install an alert system, et cetera. So we have pilots, we have software, and we have sensors. And when we combine these together in a particular way, we end up with a catastrophic failure. So this is a great example, I think, of how in medical devices it's so important for us to think in terms of not just one discipline. We don't have mechanical engineers over here doing something and software engineers over there doing something, but we integrate all of the disciplines into one cohesive view of what the controls need to be, and then we put it through the systems engineering and the risk management processes to assure that we have a complete set of controls. And so those controls and that understanding, that engineering background, doesn't get lost after we've put the device or the vehicle into service. And so what I'm going to talk about now are really frameworks. And these frameworks are different views of the control set so that we can drive a certain amount of rigor into our process and really try to get our control set to be complete. So the first one of these is really a design decomposition. How are we going to define good product? What is the construction we're going to use? In addition to that, we want to have a set of standards or reuse coming from libraries driving those controls. So there's a certain amount of design we understand extremely well for a product type, and we've built this many times in the past, so we know what we need to have into this product on some level. And we want to make sure that we use those lists of performance characteristics and we pump those back into the design so that we don't make silly mistakes from repeating mistakes that we've had in the past in different products that we've already shipped. In addition to that, we want to be able to take regulatory decomposition. So we want to be able to say, how is it, in the case of the FDA, how is it we're going to integrate risk into the control set so we can systematically walk through these controls, understand how the controls relate to one another in the context of risk. And so how do DFMEAs, fault tree analysis, that kind of thing, how does it pump back into the discussion so we make sure we have a complete set of controls to control the occurrence of hazardous situations, which then lead to harms. Finally, what do we want to do is systems modeling. And the systems modeling is a positive view of the design. We're going to deconstruct it from a operational to a systems to a logical and a physical architecture that fully develop our functional diagrams so that we can have functional chains that describe everything that's required to make this design work as we expected it to. So those are the different frameworks that we're going to take a look at today. Now, each one of these frameworks has a certain construction associated with it. So the first thing I'm going to do in this discussion is walk through those frameworks. And once we understand the context, then we'll hop out into some tools and show you how it's actually done. So design deconstruction. The FDA has a 1998 guidance document that describes how they expect to decompose a design. Now, when people look at this, they often think this is a life cycle discussion and user needs need to be developed before system requirements. And that's really not the intent here. The intent is to understand how we're going to control the occurrence of problems that would lead to a user need not being met with system requirements. Same thing with design requirements, same thing with design specifications. So essentially what we're going to do is we're going to have this refinement defined in traceability inside the tools so that we understand specifically how we're going to realize the user needs or how we're going to realize the system requirements. And we have those relationships built into it so that there's a very clear understanding of which design requirements are related to the next level up in our decomposition. Of course, this flat view of the requirements then leads to a set of test cases. Those test cases are either verifications or validations of the user needs and system requirements. So, of course, what we'd also like to do is include simulation in the test cases so that we drive a simulation-based culture. The simulation-based culture is one that looks at these controls individually as we're developing them and says, what do we need to do from a simulation standpoint to understand and be sure that each one of these controls are met before we actually move into formal testing. That way, when we come back and make a change, not only do we know what evidence we have that the device complies with our definition of good, but we also know specifically what did we do from a simulation perspective to assure that the KPIs and the specifications and the performance of the device is good before we actually went out to tool it and build it into product. Okay, so this decomposition is important. User needs to system requirements to a set of design requirements for different disciplines, and then design specifications, which are the embodiment of in the design. And what do we need to have in the design to control and assure that those design requirements are met? Okay, so the second framework is really a framework built around standards. And I'm just going to walk through this quickly so that you get a better sense of how this kind of construction happens. One of the important things as we deploy systems is we want to think in terms not just of data models. How does this work item or how does this object relate to that object? But in addition to that, we want to think about how to set these projects up in the tool so that we get the maximum reuse possible out of our portfolio. And so I'm going to start with external standards. And these external standards are things like ISO documents, ASTM documents, IEC, even some legal requirements. But the key is these are external standards that update at a cadence we don't control. And so what we want to do is pull those standards into the tool and break them down elementally. So we have a very clear understanding of each shall in one of those documents so that we can then map those into our internal normative standards. Now we're going to have a second standard library that's called normative, or our internal standards library. And what we're going to do is we're going to process those external standards in such a way as to get a clear understanding for a product type, how we're going to assure that that external standard is met. And And we're going to do that on an elemental level. So we're going to take each one of the things that have been outlined in this external standards documents, and we're going to map them into an internal standard requirement so that we understand specifically how that external standard is being satisfied. Now, one of the reasons, there's several reasons to do this. One of them is that external standards oftentimes step on one another. So we'll have a requirement in one standard that is slightly different, but sort of the same as an external standard in another document. And we want to be able to negotiate that in our internal library for the product type to be sure that we use a language that makes sense for the product that we're building, given the fact that these external standards are written for the generic case, and we want to understand how that's applied. So we're going to build out this internal normative standard library, and we're going to have all these requirements identified. Now what we're going to do is we're going to share those normative documents, which are really containers, right? When we think about documents, they're really not like a Word document. They're really a container. They contain objects that have been identified as important and testable. And so each one of these documents is a container that holds a set of either requirements or maybe risk management work items, objects, or test cases. So whatever the object is, but it's a container that holds those. Now what we're going to do is we're going to share that normative library document down into a project, and we're going to do that for whatever library documents are applicable to this particular project. Now this abstraction really makes a lot of sense, and it's very useful because what it allows us to do then is at the normative library level, whenever we get an external standard update, we can think about and process what the implication that is, what implication it has to the product that we're building, the product type that we're building across the whole portfolio without impacting the projects directly. And so I can go from a Rev A to a Rev B to a Rev C and keep Rev A that I shared to Project 1 established in Project 1 until such time as we're comfortable and we think that from a project standpoint, we want to pull that new standard down. So this allows us to come to a more clear understanding of how that's going to be done, and then take the time to approve it, run it through whatever approval cycles before we make it available to all the different projects in the company. And at the project level, what it really does is it gives us this assurance that when the time comes and we need to look at the library to see if there are new approved versions of this document, we can do that. We can do a differential. We'll understand very clearly then what the difference between the Rev A and the Rev C of the document is. And if we think it's appropriate at this point in time, we can pull that new revision down and get it updated for this particular project without impacting the rest of the projects in the portfolio. In addition to that, what we can do with these projects at the project level, or these documents at the project level, is add additional requirements that are specific only to this project. And in addition to that, if we decide we want to utilize some of these new requirements in the library, we can merge those requirements back into the normative library and improve our understanding of how this product type will implement this set of requirements over time. And so this is really, I think it was Drucker that said, the organizations that will separate themselves are the ones that are learning organizations. And this is an example of how to build learning into our development process as a matter of structure, so that as we go along and we make changes to the products over time, our normative library will become better and better, and we'll be able to take that learning and build it into the rest of the projects as we create new products over time. So this is really, how do we do reuse? How do we build that into our product set and get 60, 70, 80% of the requirements that we've built in other products built into the new products as well. And of course, not only does this create a lot of leverage from work standpoint, but it also improves the quality of the development effort, because we're not using requirements that we're pulling from scratch, that we're building new every time we do it. What we're doing is we're using requirements that were built from products that have been built in the past, and those standards have been improved over time. So we should get to a place where that normative standard library level, those requirements are super solid, have considered everything that's necessary to implement any particular requirement that's associated with the external standards over time. So a very important part of not only reduction of work, but also improving the quality of the work. Now I'm going to talk about risk management for a few minutes here, and I'm going to give you an example as we go through. Risk management is the negative view of these controls. And so the 14971 document in medical device talks about how to do a risk analysis. And this is where we're going to take harms, we're going to associate them with hazardous situations, and then we're going to create a mitigation strategy to assure that we're controlling the occurrence of the hazardous situation. So when we do this, there's a couple things that we want to get out of the analysis. The first is a residual risk analysis. After mitigation, what is the residual risk that we have associated with this particular hazardous situation harm combination? And in addition to that, we want a mitigation strategy. And I'm going to break this down hierarchically. A lot of people don't do it this way. And one of the reasons I'd like to have this conversation is to help people understand that in the extensive engagement we've had with medical device firms around the world, there is almost never a case where people implement risk management the same, even in different divisions in the same company. And so this is this discussion is intended to show the capability that's necessary to construct a system, but it's very flexible and it gives us a lot of options from the standpoint of constructing it differently. Do you want to put systems FMEAs in the design FMEA? There's a lot of different things that people do. They don't deconstruct it hierarchically. They isolate it. They don't use user needs as direct mitigations to hazardous situations, or they do. So it's a very fluid kind of situation. But I'm going to talk a little bit about how to do this deconstruction in a way, and I think you'll see why it's a powerful way to do this sort of organization of the data. So I'm going to have a harm that's infection, and we're going to have a hazardous situation is the infection. The device introduces harmful bacteria to the patient. So that is the hazardous situation that causes the harm of infection. Now we're going to have a mitigation that is the user need, and the user need is that the device be sterile. So this is our example at the 14971 level, and we believe if we present devices that are sterile, what's going to happen is that hazardous situation that the patient will be infected with the device will be mitigated. And so the user need then is very important to assuring that we have control of the occurrence of that hazardous situation. So what we're going to do then is we're going to use a use FMEA to process those user needs. And so the user need example that I have here is the device be sterile. So we're going to come up with a set of system controls to assure that that user need is met. And so in this case, we're going to say we're going to use ethylene oxide sterilization. And when we do that, what we're going to say is we need to be compliant with a certain external standard. And so the external standard that controls EO sterilization is 11135. So our system control would then be, we are going to be, the device will be compliant with the 11135 standard. So that is the system control. We believe if we're compliant with the standard, then we're going to have the ability to assure that the user need is met, that the device will be sterile. Now, one of the things to talk about here is that system control is an external standard. And so per our last conversation, that external standard would be mapped into a normative standard for this product type. So we'd have a 11135 external standard that would have a normative sterilization standard that would be a document that we could share down into the project. And the really great thing about that is then that system control of compliance with the standard would then draw into it all of the design controls that are necessary for that product type. And so we would get both the system control and all the design controls associated with it automatically populated into the project. And this is where this rich functionality for developing reuse and building these new products using standards that we've developed in the past, but this is where we get the leverage. Okay, so we do a systems FMEA that looks at the system control. Now we build out the design controls. So an example of this might be that the sterile barrier bag doesn't migrate bacteria. And then what we would do is we would process the design control of the non-migration of bacteria using a design failure mode analysis and come up with a set of design specifications to assure that our design performance is built in a way that controls that design control. So now we would say the design specifications might be things like we'll have a sterile barrier bag with Tyvek, and using Tyvek for the gas migration, and we might have a 3/8 inch bag seal as an example. So now what's really important here now is we have a total design control plan where we've identified each level of control and what's necessary from a progression to get to the level where we have the design, the actual characteristics of the design defined. And if the traceability shows that those characteristics then lead directly to a hazardous situation harm combination that is of high risk, then we can get into a spot where we understand that those design specifications are critical to quality characteristics and should be then processed through a process failure mode analysis to get the set of production controls to assure that we have control of the production process as well. So then we'd have our inspections and our process controls like heater band temperatures or measurements of the product to assure that we have those production controls in place to assure the design specifications have been met. Now, if you look at this entire thing, not only do we have a control plan for the design, but we also have a control plan and an inspection plan for the production. And this is our entire causal chain now of how a hazardous situation could possibly occur with our design, including the use of the design, meaning labeling and training, the systems controls, the design controls, specifications, and production controls out through the manufacturing process. And of course, when we're finished with those production controls, we would include them in the manufacturing process planning, which would then get them into the bill of process, and the bill of process would then be shared to the manufacturing execution system. So we have a total closed loop on everything that's required to make sure that this device is safe. Now you can imagine that if we had a problem in the field where we had a failure, that problem would come back into the risk management, and each one of these FMEAs would have occurrences associated with them. And we would be able to say, did we understand and process the design in such a way as to consider this problem we've identified in the field? And in addition to that, we would have occurrence rates that we could compare to the occurrence in the field to understand whether our mitigation strategy is working well or not in the context of this residual risk analysis that we did at the very top level. So all of this construction is really very important to building our understanding of product and how the product can fail, so that as we do our post-market surveillance activities, we have a place to land that data. It becomes the contextual key of the data that we're bringing back from the field. Now, the last thing I'm going to talk about here is really associated with the systems modeling. And in systems modeling, we really have three different types of data that we want to be concerned with. So the first one is the set of design controls. Now, these design controls are requirements, and they're a flat view of what we need to do the testing. So as we enhance this model, the idea is when we're done with developing these controls, we'll execute our test management system, and not only will it say, did we meet our set of controls, but also it will assure that we've mitigated all the hazardous situations that we've identified in our risk management system. So the testing serves a dual purpose. So we have the design controls. Now what we want to do is take a positive view of the design. What does the design need to do in order to give us the performance that we designed it to give us in the first place? So when we do systems architecture, then we're going to pull in all of the different interrelationships of how the system should work, and we're going to do that through a series of analyses. So we're going to do an operational analysis, which is really looking at the entire design space. We're going to do a systems analysis, which breaks the system that we're building out from the overall design space and helps us understand the context of what's in the box and what's out of the box, literally. We're going to do a logical analysis, and then finally a physical analysis. And that physical analysis is going to give us a set of functional chains that can then be interrelated with the comprehensive bill of materials, so that we can drive that systems engineering into not only the bill of materials from a physical architecture standpoint, but also into the design specifications. So when we are looking at the user needs, the system controls, and the design specifications, this system architecture informs those controls as to how they actually ought to operate. So you can imagine if we're doing for example, we're doing an FMEA, the first thing that we want to look at from an FMEA standpoint is all the functions that are associated with any particular system control, so that we know specifically what are the steps in that process that we want to analyze. Not only what are the steps, but where do those steps in the form of functions, where do they reside in the system? Are they in the box that we're selling somebody, or are they in an iPad application, or are they in a cloud, or are they being accomplished by a user? And when we understand where those functions are and how they relate to the system controls, decomposition of the systems controls to design controls, design specifications, and production controls becomes much easier and much easier to understand from a complexity perspective. And then, of course, those design specifications then are related to the bill of materials. They're consumed in the bill of materials, and that allows us then to go ahead and do our PFMEA activities, our inspection control plans and whatnot, to get to a place where those design specifications are built into our manufacturing execution system. So hopefully this framework discussion kind of gives you a better sense of all the different components. Now what I'm going to do is pop out and we're going to get into some of these tools and start talking about how to actually build it into tools. So thanks so much, and we'll talk on the next one.